Let us start with the next point of a group theory, that is factor group. In previous lecture we studied a normal subgroup of a group G and its equivalent properties. Then using of normal subgroup we define a factor group under the binary operation. For that purpose we first upon define one corollary. Then consider the statement of corollary. Let H be a normal subgroup of a group G, then the coset of H forms a group G by H. What is G by H? It is factor group, where G is a group and H is subgroup. What are the binary operation that forms a G by H group? Then the coset of H forms a group G by H under the binary operation. Left coset AH into BH is equals to ABH. Then we first prove that under that binary operation that factor group G by H forms a group. What is the set G by H? G by H, it contains a set of all cosets, say GH, where G belongs to G. Then claim is to prove that G by H is a group under defined binary operation. Now G by H is non-empty. Why? Since a subgroup H can be written as in terms of coset EH and E belongs to G. Since G is a group, therefore EH belongs to G by H. G by H चे एलिमेंट कसे असतात? तर कोसेट असतात. कोसेट कसे फॉर्म करतात? हा H हा सबग्रुप ॲज इट इज आणि हे कोसेट फॉर्म करणारे एलिमेंट कोणाचे असतात? ग्रुप Gचे असतात. म्हणजे G by H काय तुमचा नॉन एम्प्टी आहे. नाव फर्स्ट फ्रॉम द डेफिनेशन that AH into BH is equals to ABH, and for AB belongs to G, then A into B also belongs to G. Since G is group, then by closure property for any AB belongs to G, AB belongs to A comma B belongs to G, A into B belongs to G. Therefore first property is hold. Now to prove that the associative property, let AH, BH, CH are the element of the factor group G by H. Then AH into round bracket BHCH is equals to AH into BCH. Again that A and BC are the elements of group G. Then by using associative property, it can be written as A right down to bracket BCH, which is AB into CH, which is equals to the square bracket ABH into CH by associativity in group G, which can be written as AH BH from the definition into CH, and hence the associativity hold in group G by H. Now consider the existence of identity, that is AH into H, that H can be written as EH. Again from the definition, AH into BH equals to ABH, therefore it becomes AEH is equals to AH, which is same as HAH. Therefore EH, that is H, is identity element of group G by H. Identity element of G by H group आहे आपण प्रूव्ह करतो. Now next to finding inverse, suppose AH belongs to G by H, then we have to find out inverse of element AH. A belongs to G, there exists A inverse belongs to G, such that A into A inverse equals to identity. Then AH into A inverse H can be written as A into A inverse H. By the definition, it is EH equals to H, which is same as A inverse H into AH. Hence AH inverse is nothing but A inverse H. Hence G by H is group. Therefore we prove that the set G by H forms an element of a coset, that is AH, A belongs to G, with binary operation AH BH equals to ABH, is called a factor group or quotient group by G by H. In previous example we proved that G by H is group, and that G by H group is called as factor group or quotient group. Now we see the examples of factor group or quotient group. If G is abelian group and H is a normal subgroup of group G, then G by H is abelian group. It is famous example, that is in previous lecture we say that if G is abelian group, then any subgroup of abelian group must be normal. That is, if G is abelian group, H is a normal subgroup of group G, then G by H is also abelian group. Now to prove that G by H is abelian group, that is we have to prove that any two coset in G by H are commute under the binary operation. Since G is abelian, H is subgroup, H is normal subgroup of group G. Therefore, that AH BH equals to ABH is well defined property, and also we prove that G by H is group. Therefore, here nothing to prove that G by H is group, since in first example we prove that G by H is group under the binary operation. Only remains to prove that the abelian property. Then for any AH comma BH belongs to G by H, AH into BH equals to ABH, but that AB is element of group G and G is abelian, therefore AB can be written as BA, therefore this can be written as BAH. Then by definition it is BH AH, therefore G by H is group and it is abelian group, therefore hence the factor group G by H is abelian group, and we prove the result. That is, if G is abelian group, H is normal subgroup, then its factor group G by H is abelian. Hence in that section we prove that a factor group of abelian group is abelian. It is important property of factor group, that is factor group of abelian group is an again abelian group. Now we let us next we discuss a small example, that is actually it is theorem. That theorem says that if H be a normal subgroup of group G, then mapping gamma from G to G by H given as gamma of X equals to XH, it is an homomorphism, and having the kernel is normal subgroup H. It is important theorem or property that a mapping from a group G to factor group G by H, provided that H is normal. H is normal, hence G by H is factor group defined as gamma of X equals to, let coset XH. It is homomorphism as well as kernel of that mapping, it is H. Now we prove the result. For XY belongs to G, then gamma of XY from the definition, it is coset XY into H, which is equals to XH YH, since H is normal subgroup, and from the definition of coset it is defined as ABH equals to AH BH. From that definition XYH it is defined as XH YH, since H is normal subgroup. Therefore XH is nothing but gamma of X, YH is nothing but gamma of Y, therefore gamma of XY equals to gamma of X into gamma of Y. Hence prove that the mapping gamma, it is homomorphism under the mapping G to factor group G by H. Now next claim is to prove that kernel of that mapping, it is nothing but H. Now what is kernel? Kernel is H. Since H is normal subgroup, then kernel contains all that element X such that, what is kernel of that mapping? It is contains the set X belongs to G such that gamma of X equals to identity in G by H. That is identity in G by H, that is 0H. That is we have the property gamma of X equals to H. Gamma of X का है XH, that is XH equals to H. Hence XH equals to H. Then by property of coset XH is equals to 0H if and only if X minus 0, that is X belongs to H. Hence it is hold if and only if, that is if X belongs to H. Here we prove that if X belongs to kernel of H, then again X belongs to H, and also same as the kernel of element in the subgroup H, it also belongs to kernel of H. Hence it is if and only if, therefore the all elements are nothing but element of H. Hence kernel of gamma is nothing but the whole subset H. Hence we prove the result. Remember that example for solving the exercise or solving the question related to the kernel. We again summarize the theorem. Theorem says that if H is normal subgroup of group G, then the mapping gamma from G to G by H is given as gamma of X equals to XH, and it is homomorphism with kernel capital H. So in the next In the next video, we see the next fundamental theorem of homomorphism depending upon the kernel and the mapping homomorphism.